Well, thanks first to the organizers for inviting me, then thanks for coming after lunch. So I will talk about colorful simplicial depth. There will be colorful point configurations, just like this one in the picture. And then there will be also Minkowski sums. We heard about them this morning, and some Gale transforms. And this is some joint results I have with Karima Di Prasito, Philip Brinkman, Pavel Patak, Zuzana Patakova, and Raman Sanyan. So I'll start by telling you the main result and its story. So the way to start would be by Carathodory's theorem. So what does Carathodory's theorem say? It says if you have a subset of Rd, like in my case I called it A, and it's this gray point, and you have a point X in its convex hull, then you can find a subset of at most D points, D plus 1 points whose convex hull contains this point. So this is Carathodory's theorem. And this is Barany's colorful version of this theorem. And now instead of one point set, you have D plus 1 point sets. We can imagine them, usually imagine them as you have a point set where the points have colors. So here I have the red point set, the green point set, the blue point set. Each one of them will contain the origin in its convex hull. So my point X will usually be assumed to be the origin. And then the colorful Carathodory theorem says there is a way to pick one point from each color class in such a way that the origin is contained in the convex hull of this simplex. So this is the way I like to state the theorem. Any centered colorful configuration contains one heating colorful simplex. So for me, a colorful configuration will be just what we had right now. So D plus 1 subsets of Rd, they will be always finite. Which one, I'll think about it like being of a different color. So this is a colorful point configuration. It is centered if each color class contains the origin. So actually for this theorem, you can weaken the condition of being centered, but I'll keep the condition, let's say the original condition by HUN-REN. Then it says that it contains a heating colorful simplex. A colorful simplex will be one whose vertices are all of different colors. Right? So here this was a colorful simplex. By my definition, this edge is also a colorful simplex of one dimension less. And it will be heating if it contains the origin of its convex hull. Actually, what I really want is the relative interior of the convex hull, and avoiding otherwise. And actually, for the whole talk, I will assume that things are generic enough. That makes my life easier. So this relative general position, for example, it's enough if we assume that there's no low-dimensional colorful simplex that contains the origin. So I would not allow to have the origin here, for example. Well, some things can be avoided. You don't really need to do this, but it makes my life easier. Okay. So then a natural question, once you have that there is one colorful simplex, is to ask how many are there. Right? So the colorful Carathodory theorem says there exists at least one heating colorful simplex. Natural question, how many are there? And this is called the colorful simplicial depth. So this name, I think it was coined by Deza, Huang, Stefan, and Terlaki in a 2006 paper. And they looked in particular to the case where each color class is a full-dimensional simplex that contains the origin. And they conjectured that the depth is always between, in this case, so each color class it's a simplex, has D plus 1 points, that the depth is between D squared plus 1 and 1 plus D to the D plus 1. And let's see so both bounds if correct, they are tight. So they constructed configurations for the two sets. And there's been more or less a race to prove the lower bound, which is probably the more interesting part of the question. And it actually already, Imre Bárényi's colorful Carathodory theorem, his proof gave d plus 1, not only 1. Then when they posed the conjecture, they managed to prove that there's always 2D colorful simplices containing the origin. And then we had the first quadratic bound, and there was a series of papers improving the constant for this quadratic bound until the last one where Pauline Sarabezol 2 years ago managed to prove this conjectured lower bound. But for the upper bound there was no progress, and so the main result could be seen as proving this theorem in a generalized way, in the sense that I won't assume anything about the sizes of the colors. So their question was for size d plus 1, but actually the proof works for any size. Here, of course, this only makes sense if you have this centered condition, right? Otherwise, you can have all colorful simplices to be hitting, right? So the question is, how does this centered condition restrict you? And the answer, which was already the one they conjectured, is the obvious one, right? So this is the configuration where everything is hitting, but it's not centered. If you want to make it centered, the obvious thing to do is just to add one antipode to each of these clusters. Now each color class is containing the origin. And here, how many colorful simplices do you have that hit the origin? Well, there's this one, which is isolated. And then take any of here, any of here, and any of here, and you'll get a colorful simplex that contains the origin. And this amounts to this 1 plus the product of the sizes minus 1. Okay? So, and this is what we'll prove. Okay. So actually, these first slides that makes a very nice story and a good motivation for why should one study this problem, and why should one solve it, and why our result is interesting, but it's very far from our real interests. So we didn't know about this conjecture when we started working on it. What we did know was something completely different. So instead of giving you the proof, I'll spend some time giving you how did we reach this problem, and why did we get interested. I don't claim that my motivation is the good one. Actually, to convince you, I put these slides beforehand. But anyway. So our problem starts with Benjamin Barton's PhD thesis in something I don't know anything about. And in some page, he has some conjecture that says d minus 1 is equals 1 plus 2 to the d minus 1. So I don't even know what d minus 1 is. I know one interpretation in terms of arrangements of funds. But of course, I didn't read Bern's thesis, but the way I reached to this is an email he sent to Gunther Ziegler in, I think it's 2012. And I only read you how it starts. It says, "Dear Gunther, I have a problem that has been puzzling me for several years now, involving combinatorial arrangement of geometric objects built from half space in Rn." And then he says, do you have any insight? So Gunther then forwarded this email to Raman Sanyal, and this is essentially how I reached it. When it reached me, there were no U and no projective edge-weight solution spaces in normal surface theory at all. Okay, so I'll explain you my version of the problem, but like the first picture we got was something like this. So there are some collections of funds like these ones, and you want to count the maximal number of intersections like these ones. Okay? The way to transform this into a problem of polytopes, which is what I do for living, is Minkowski sums. And just to drop the keywords, to go from fans to Minkowski sums, the keyword is the normal fan. So if you have two polytopes and you do the Minkowski sum, the normal fan of the Minkowski sum is the common refinement of the two normal fans. And these are actually normal fans of certain polytopes, certain triangles, and the things we are interested, these intersections, come from some faces of this Minkowski sum. So let's speak directly about Minkowski sums of polytopes. We've heard a lot, so I don't have much to say. The Minkowski sum of two polytopes is just to make the pointwise sum of the two sets. So for each point in P and each point in Q, you take the point P plus Q. And for example, for this triangle and this square, you get this polytope here. So all my polytopes will be convex. You don't need your things to be full dimensional. For example, I can add two triangles in R3. This is where I get some, let's say, degenerate normal fans that look like what we had before. And the observation is that each phase of the Minkowski sum arises as a sum of a phase of one of the polytopes plus a phase of the other polytope. So for example, here, this phase is the complete triangle times 3, right? So it's 3b, 3a, 3c. And then, for example, this phase here is the sum of this edge here with this edge here. So each phase of the Minkowski sum is a sum of one phase of each of the two polytopes. Okay? Could be the complete polytope. And of course, not every pair of faces gives rise to a phase of the Minkowski sum. So if we translate Ben's problem to Minkowski sums, then it reads as follows. So you have triangles in RD, actually d minus 1 triangles in RD, and you want to count what we call totally mixed facets, which are simply facets of the form edge plus edge plus edge plus edge. Right? So in the three-dimensional case, we have two triangles in R3. We do the Minkowski sum, and we count how many faces are of the form edge plus edge. And he wants to know what is the maximal number of such faces. Right? So here I gave you two examples. In this one, we have 5 totally mixed faces. In this example, we have 4. So this one, and this one is actually the upper bound. And he conjectured that this number is at most 1 plus 2 to the d minus 1. So in the case of d equals 3, that's 5. So this is the conjecture upper bound. So this is the problem as I got it. Let's say it like that. And so this is the first. So it's already, you can see already some colors, right? So at the end, I want to say that this conjecture is more or less equivalent to the one we solved. And so I have to find the colorful point configurations and heating simplices, etc. Well, here you already see some colors. I'll put them together in what's known as the Cayley polytope. The Cayley polytope is, let's say, for me, a combinatorial way to deal with Minkowski sums, or a geometric way. So you have several polytopes. You want to study its Minkowski sum. What you can do is to study a single polytope. You just take, for each point in Pi, you take, let's say, standard basis vectors, so the vertices of a simplex, and you take the convex hull of EIP, where I is different depending on which was the original polytope this P came from. I'll show you an example. If you have two polytopes, then essentially these EIs, they span a segment. So you have only like two possible values for this first coordinate. So you'll just embed, for my sum, which was a square plus triangle, you embed your square at height, let's say 0, and your triangle at height 1. So this is the Cayley polytope of a triangle and a square. So this Cayley polytope has several interesting properties, in particular in terms of triangulation and mixed subdivisions. But what I need is something very simple. It's just the Minkowski sum of your polytopes appears as a slice of the Cayley polytope, which is what I tried to draw here. The Minkowski sum, so I had it here, of this triangle plus this square is this shape, which appears here as the middle of these two, the triangle and the square. If you have several polytopes, it's not a hyperplane that you're intersecting with, but some lower dimensional subspace. But there's always this kind of behavior. And one way to read this is, once you have your Cayley polytope, I can find the phase lattice of my Minkowski sum as follows. Just look at your Cayley polytope and look at the faces that touch all colors. So what do I mean by that? Like, for example, here I have one vertex, and so I look at the vertices of this face, this triangle. They touch red and they touch blue. That means that that will induce a phase that will be cut by this hyperplane. So that will induce me a phase of the Minkowski sum, which will be the Minkowski sum of this vertex with this edge. Right? Then, for example, this edge here, again, is a phase of the Cayley polytope that touches all colors. So this will induce me a vertex of the Minkowski sum. Whereas, I don't know, for example, this edge here, it's monochromatic, so it's not inducing me a phase of the Minkowski sum. So now it starts to get colorful. I will work only with the Cayley polytope. And my last ingredient is Gale duality. So this is a super brief introduction to Gale duality. Essentially, if you know it, good. If not, don't worry, because I'll go on. It's not really needed. Essentially, for Gale duality, you start with a configuration of n points in Rd, and it gives you another configuration of n, actually, vectors in Rn minus d minus 1. So if n and d are very close, this is very interesting because it gives things low dimensional. And you probably know this example by Perles of a non-rational polytope. This is what he used. Right? If n and d are very close, then the Gale transform is low dimensional, and it's something you can deal with. But in any case, you start with your n vertices, and you get another set of n vectors, where you can read the whole phase structure in this transform. So you don't lose information. You have all combinatory information. The way to read it is if you have a subset of vertices that will form a phase, if and only if, here I should have a relative interior. If and only if the origin is in the relative interior of the convex hull of the complement of, so here I have those that are indexed by I, and here those that do not have a label in I. It's not really important, but that's what I use. So what is interesting is that if you take a Cayley polytope, then you have your Gale transform. It's naturally a colored point configuration because each vertex had already a color in your Cayley polytope. And it also, if you look at it, actually the characterization of being a Cayley polytope is exactly being centered. So here we have already the first thing. And now this is just a dictionary. So we have essentially an equivalence between Cayley polytopes and center colorful configurations. And you can translate the properties of being a phase or being a totally mixed phase, etc. So just to show you that this works, this is this Gale dual of the Cayley polytope of the sum of these two triangles. For example, the fact that 2 and B contain the origin in their convex hull, that means that the complement, which is AC31, forms a phase of the Minkowski sum. So let's see AC31, the sum of A3 with 3,1 is actually a phase of the Minkowski sum. Right? So for example, playing with this that is now one-dimensional, we could prove that this upper bound for three-dimensional triangles works. This is what we call the colorful Gale transform. And this is just a dictionary, but sometimes dictionaries are useful. And in our case, there's some genericity assumptions, but essentially being a colorful heating simplex is the same as being a totally mixed facet. Hence, our theorem on colorful point configurations and the upper bound for the number of heating colorful simplices, it's also an upper bound for the number of totally mixed facets of Minkowski sums of simplices. And so this is just more or less a translation under these genericity assumptions. If you have that all your simplices are triangles, then these are all 2, and then you get this 1 plus 2 to the something that we had in Ben's conjecture. So this is it. Actually, we wanted to prove this conjecture of Minkowski sums of triangles, and then we managed to transform it into a problem on colorful point configurations. The first there was the hope maybe it's already solved for colorful point configurations and there's nothing to do, but it was actually more or less the same conjecture posed in that setup, so we had to prove it. The only difference is that it was posed for all color like point sets having size d plus 1, and here the point sets have size 3 because they come from triangles. Okay, so we'll have to prove it. And the proof will be topological. So I'll just say some words about it. You can forget about everything I just said except for the problem, right? We have a colorful point configuration. Each color class contains the origin. We want to find an upper bound for the number of simplices that are colorful and contain the origin in the convex hull. And we have this relative general position assumption. Okay, so I'll work with two simplicial complexes. So one is K, is the colorful complex, is the simplicial complex of all colorful simplices. It's just the join of all color classes. So something will be a simplex here if and only if all its vertices are of different color. Like for the case where all the sets have size 2, this is just the boundary of an octahedron. So this is the colorful complex. And then I have the avoiding complex, which is the simplicial complex of all the simplices that avoid the origin. The fact that I have these genericity assumptions already tell me that this is a simplicial complex, which will have a complete, not complete, but it will have the same d-1 skeleton as this one, right? And there's only some full-dimensional faces that are missing. Like for this example, there's only 2 faces of this octahedron that I remove because these are the only 2 triangles that contain the origin in the convex hull. So these are my two complexes. And now I'll study the Betti numbers of these complexes. So we work with Z2, but just because we didn't need more. And for the complete complex, the colorful complex, that it's not hard to do. It's actually a wedge of spheres. So it has Betty number 0 for everything of dimension lower than D, and it's this Ci minus, the product of Ci minus 1 for k equals D. This is just because this was a join of these joint point sets, and you just do it. But this was the complete thing, and then I have only my avoiding thing, where I have to remove those simplices that were hitting the origin. So that's the only difference between these two complexes. So what I'll do is to compute the Euler characteristic first as an alternating sum of faces, and then as an alternating sum of Betty numbers. So for if I do faces, that of avoiding and that of the complete thing, the only difference are the heating simplices. And the heating simplices, by definition, is the depth, which is the number I'm interested into. Right? So this gives you this part of the equation. And then I can also do the alternating sum of Betty numbers. Here, if I do it with k, I have the exact Euler characteristic because I do know the Euler characteristic of k. If I do it with a, well, I just removed some things of full dimension that only can affect only two Betty numbers. It can change the d minus 1 or the d, but the rest remain unchanged, and they are all 0. And now you just reorganize this equation here, and you get that actually the depth of our configuration is always exactly this product of Ci minus 1 plus the Betty number d minus 1 minus the Betty number d. This just it's like that. But this looks very similar to what we wanted. And actually, so this is always non-negative. So this gives you an inequality. So if this is always non-negative, this is always at most this. So if I prove that this number is 1, I just get the upper bound I was looking for, which was this product plus 1. Do you agree? So this is what we prove. Actually, this is what we want to prove. And so to prove that this is at least 1 is not hard, because we already have one colorful simplex that contains the origin. This is actually the colorful Carathodory theorem. So this is already giving me one cycle of dimension d minus 1, and where is more difficult is that there is only one. And to prove it, we prove two things. So first, we prove it for our favorite configuration, which was the one I showed you before. So let's try to work it out. Who is the complex for this configuration, which is essentially a big cluster here and an antipodal point, a big cluster here, an antipodal point, a big cluster here, an antipodal point. So these clusters are, let's say, on the vertices of a simplex, and then the antipodes are on the opposite simplex. So if the clusters were all of size 1, I already showed you this picture here, right? Is this just, you have an octahedron and you have two simplices that are removed, these two. So, for example, here you already see that in this case, topologically, you only have one cycle, right? If you have several points here, that doesn't make much of a difference, right? So if I add a new point here, I will add it to, so this one and this one, they behave equally. If I add a new one, I will just look at the link of let's say, this vertex, and cone over that with a new blue point. And so this is actually the complex. I don't know if your picture, if this picture makes sense to you as it does to me. So here it says just take any of the points in this cluster. And here it says take any of the points in this cluster. And here it says take any of the points on this cluster. Right? So this is giving you all the avoiding simplices of this configuration. And as you can see, up to these repeated points, this is just the octahedron removed two antipodal faces. And to prove that this is actually the same as a cycle, you can actually just collapse it to this heating, the boundary of this heating simplex here. So you first look at all the simplices that contain two, let's say, vertices from clusters. These you can just push here onto these two edges, and you can just homotopy is the same, and then you do it for this one, and then you do it for this one, and you are left with only these three triangles over here. And you can do the same now. You just push from this vertex onto this edge, and at the end you can just retract everything to this the boundary of our heating simplex that we had at the origin. So for this configuration, I hope you are at least convinced that it works, that we have the Betti number is 1. And to finish, so the main part of the proof, which is something I don't want to tell you because it's more messy, what we just do is just prove that this property is preserved when we do flips. So the essential idea is you have your favorite center configuration. You can transform it to my favorite, which was this one, and just move each color class independently. So you don't want to lose the property of being centered in the process. So you just take each color class and you move it independently. And essentially, if you do this generically enough, the only things that will happen is that at some times, the origin will cross some, a colorful ridge. Right? So we'll cross a colorful phase of dimension 1 less. And then here, what happens is that all these simplices here that used to be heating, now they are avoiding, so I'm adding them to our complex. And all these simplices here that used to be avoiding now are heating, so I'm removing them from my complex. So this is creating me new cycles. I have to prove that they are all equivalent. This is the point where this centeredness assumption is crucial. Of course, it has to be there at some point, because if I take everything in a different cluster, I do not have my upper bound. So I have to use it somewhere. And this is here. So the fact that it's centered, that tells me that if I take a hyperplane along this ridge, each color class will have at least one point at that side, right? So I know that at this side, there's at least one green and one blue. And now to prove that these two simplices are equivalent, these two cycles are equivalent, so I assume that there's at least two red too. And now if you look at this closely, this is actually just another octahedron as the one we had before, where you take out two faces. So again, these two cycles, they are equivalent. And that's essentially it. So the rest is just like writing it up. And I think I'm finishing early. That's it.